Hello Math 110 students. I've created several YouTube videos going over the course content and how the class works is I will go over in the order of the book chapters 1, 2, 10, 11, 13, and 14. We're going to go in that order. And we'll have tests every 2 chapters. Okay, so that'd be 3 tests total. Okay, so a test every after chapter 1 and chapter 2, a test after chapter 10 and chapter 11, and then a test after chapter 13 and chapter 14 is what I'm looking at there. I'm going to start chapter 1 now. We're going to do the first 3 sections in chapter 1. That's 1.1, 1.2, 1.3. 1.1 and 1.2 are all about inductive reasoning and problem solving. And the problem solving part of this is I guess, what section 1.3 is all about. So let's get right to it. If we consider the following list of numbers, determine the most probable next term in each list. Okay, so for example, if we have part A, 13, 17, 21, 25, 29, what will be the next term that you guess? Well, it looks like we're going in an increment of 4. Okay, so I guess 33. Part B, what if we have 1, 4, 9, 16, 25? Okay, well, it looks like we have square numbers. Okay, so like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. You guess that trend would continue, and so 6 squared would be 36. Okay, part C. What if we have 1, 1, 2, 3, 5, 8, 13? We call this sequence a Fibonacci sequence, and a Fibonacci sequence is basically where you're just adding the previous 2 terms to get the next term. Okay, so check it out. If I take 1 plus 1, I get 2. 1 plus 2, I get 3. 2 plus 3, I get 5. 3 plus 5, I get 8. 5 plus 8, I get 13. So you guess that trend would continue. 8 plus 13 gives me 21. Okay, so 21 would be, an educated guess there for the next term. Part D, what if we have 2, 6, 12, 20, 30, 42? Okay, what would be the next most probable term in that list? Well, let's see. So it appears that in this sequence, I am increasing the number that I'm adding to each term there. Okay, so if I go 2 to 6, I added 4. If I add 6 to, if I add 6 to 6, I get 12. If I add 8 to 12, I get 20. If I add 10 to 20, I get 30. So I'm basically increasing the number by 2 there each time. So if I add, if I do that again, increase by 10. So I just increased by 10. If I add 12 now to 30, then I get 42. Okay, so if I add 14 to 42, I get 56. So 56 would be a reasonable guess. Okay. Part E, 27, 21, 16, 12, 9. Okay, so we're using a pattern. Okay, and looks like, okay, if I go 27 to 21, that's 6. 21 to 16 is 5. 16 to 12 is 4. 12 to 9 is 3. Okay, so it looks like I'm just decreasing the increment by 1 each time. So I just had an increment of 3. What if I had an increment of 2? And I'm subtracting, of course, so 9 minus 2 would give me 7. So I'm observing a pattern, and based on the pattern, I can predict what the next most probable number is. Okay. Now there's some problems in the book that are going to be where they won't give you a list of numbers, but they'll give you a list of equations, and they want you to determine the next most probable equation in the list. So if we do a couple problems like that, part A, okay, 1 times 9 is 9, plus 2 is 11. 12 times 9 is 108, plus 3 is 111. Okay, 123 times 9 plus 4 is 1,111. Okay, and now it looks like all I'm doing here is I'm increasing this number. And by the way, each time it's going to be a times 9, and then I'm just increasing the number of ones that I see on the right. So I think I want 1, 2, 3, 4, 5 times 9, and then plus 2, 3, 4, 5, 6 is equal to it's going to be 6 ones then. Okay, and of course I can check that, using my calculator. If I take 12,345 times 9 plus 6, I should get 111,111. Okay. Part B. Okay, if we take 3 equal, so same deal. We're trying to guess the next most probable equation there. If we have 3 equals 3 times 3 minus 1 divided by 2, well, 3 minus 1 is 2, so 3 equals 3. Okay. 3 plus 9 is 12. 9 minus 1 is 8. Divided by 2 is 4, so 3 times 4 is 12. Okay. 3 plus 9 plus 27 is 39. Okay, and if I take 27 minus 1, that's 26. Divided by 2 is 13. Times 3 would also be 39. Okay. 3 times 9, or 3 plus 9 plus 27 plus 81, that would be equal to 3 times the quantity, 81 minus 1 divided by 2. Okay, so what's the next most probable equation is the question there. Well, it looks like on the left I have powers of 3. Okay, so like 3 to the first is 3, 3 squared is 9, 3 to the third power, 3 times 3 times 3 gives me 27, 3 to the fourth power, 3 times 3 times 3 times 3 gives me 81. So I guess that the next term that I'd add would be 3 to the fifth. Okay, 3 times 3 times 3 times 3 times 3 should be 243 if you were to check that. Okay, and if you were to add these together, now it looks like on the right, you're always going to be starting off with a 3 in the numerator and then a 2 in the denominator. And it's going to be whatever this last number was, leading off inside the parentheses, minus 1. Okay, so I said 243. Okay, so it's going to be 243 minus 1 is 242. Okay. Times 3 divided by 2. So if you were to check that, I think you'd find that the answer would be the same on both sides there. Okay, and by the way, I'm using an equal sign here, so of course the two sides are equal. Okay, of course I don't want to be using that if indeed something is not true there. So as a note, using a pattern is nice for making a prediction, but keep in mind that you are just guessing the next likely term. Okay, that's all I'm doing here. I'm just guessing the next term. Like how do I know that I guessed wrong? I mean, like who knows? Like maybe the next term here is 28. Okay, well 33 would be a reasonable guess. Okay, but so who knows though? It could be 28. It could be anything. So the conclusion may or may not be true. Okay, that's important. So problem 3, part A, we're going to count the number of regions inside of each circle. Okay, so I've got a circle and 1 point on the circle, and 2 points and 3 points and 4 points and 5 points, and then different lines are connecting these points. So, okay, how many regions are inside of each circle? Well, there's one region there. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 1, 2, 4, 8, 16. Okay, well, it would be reasonable for somebody to guess that the number of regions that are in a circle where there's 6 points, okay, because right here I've got 5 points, and I'm connecting each point with all the others, would be 32, right? Because 32 would be like it looks like I'm just looking at powers of 2. Okay, well, let's check it out. So if I look at 3b there, based on the results from part A, how many regions do you think there are inside the circle below? Okay, so I've got a circle there, and there's 6 points on the circle, and now like I said earlier, it'd be reasonable to guess 32, okay, just because of the trend there, where I was going 1, 2, 4, 8, 16, 8, 32 would be my guess, okay. But if you were to count that, okay, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25, 26, 27, 28, 29, 30, there's 31 there, 31. Well, now 31 is correct. Okay, so if I would have guessed 32, I would have been wrong. Okay, and the point is that you want to be careful about what you're doing. Okay, don't assume that your guess is true. Okay, it might not be. Okay, and so that kind of that idea takes me to inductive reasoning, where it says that inductive reasoning is characterized by drawing a general conclusion from repeated observations of special examples. Okay, the conclusion may or may not be true. That is important. Okay, just like up here, if we would have guessed 32, we would have been wrong. Okay, deductive reasoning is characterized by starting with a general principle and then applying a special example. Okay, so the main thing that I like to do here is just determine if there's a pattern being explained in the problem. I mean, because that's really what inductive reasoning is all about. It's all about a pattern. Okay, if you go from the special case to the general principle, then you're using what's called inductive reasoning. Otherwise, if you go from a general principle to a special example of that, then you're using deductive reasoning. Okay, so that's kind of what I want to look for here. So let's determine whether the reasoning is an example of inductive or deductive reasoning. Okay, problem 4. My dog barked and woke me up at 1:02 a.m., 2:03 a.m., and 3:04 a.m. So the next time he's going to bark, he's going to wake me up at 4:05 a.m. Well, that'd be an example of inductive reasoning, okay, because there's a pattern going on there. Okay, 1:02, 2:03, 3:04. So you guess, based upon this pattern, 4:05. Okay, now again, the conclusion may or may not be true. So we're not saying that the dog's going to bark at 4:05. Okay, we're saying that it's reasonable to guess 4:05 based on the trend there. Okay. Problem 5. A company charges a 10% restocking fee for returning an item. So when I return a printer that costs $150, I will only get $135 back. Okay, well that's an example of deductive reasoning. Okay, and so deductive is where you're number one, you're not given any pattern whatsoever. And so the next thing that you want to think about is if you're going from the general case to a special principle. Okay, well, in general, everybody is going to be charged a 10% restocking fee for returning an item. Doesn't matter who the person is. Okay, so now the special example is you are going to return a printer that costs $150, and so you're going to be charged the 10% restocking fee, and so you're only going to get $135 back. Okay, and yeah, that'd be an example of deductive reasoning. Problem 6, if you take your medicine, you'll feel a lot better. You take your medicine, therefore you'll feel a lot better. Okay, so again, the general to the special situation is what I'm looking at here. So there is no mentioning of any pattern at all. Okay, which actually means I can probably rule out inductive reasoning. Okay, so in general, anybody who takes medicine, they're going to feel a lot better. Okay, now the special example is you're going to take medicine, therefore you will feel a lot better. Okay, that's deductive reasoning. Problem 7. Carrie's first 5 children were boys. If she has another baby, it will be a boy. Okay. Well, that would be an example of inductive reasoning. Okay, and because I am given special cases, and so I'm gonna show that in general now, I believe that okay, if she has another baby, it's gonna be a boy. Okay, so the first 5 children were boys. Okay, if she has another baby, well, it's gonna be a boy. Okay, now again, we're not saying that it is gonna be a boy. Okay, the conclusion may or may not be true. Okay, so it's reasonable to guess that it is a boy based on the trend. Problem 8, if the same number is subtracted from both sides of a true equation, then the new equation is also true. I know that 9 plus 18 is 27. Therefore, 9 plus 18 minus 13 is equal to 27 minus 13. Okay? So that would be an example of deductive reasoning. Okay? I know that the same number is subtracted from both sides of a true if the same number is subtracted from both sides of a true equation, then the equation is also true. Okay, that's true for any equation. Okay? So you're starting off with something that in general is gonna be true no matter what. Okay, and then now the 9 plus 18 equals 27, where you're subtracting 13 from both sides. That's the special example. Okay, so that's deductive. Problem 9. For the past 126 years, a rare plant has bloomed in Colombia each summer, alternating between yellow and green flowers. Last summer it bloomed with green flowers, so this summer it's going to bloom with yellow flowers. Okay, so that would be an example of inductive reasoning. So for the past 126 years, a rare plant has bloomed in Colombia. It's going to alternate in colors, so it's yellow, then green, then yellow and green, right? So it's reasonable to guess that since last summer bloomed with green flowers, then this summer's going to bloom with yellow flowers. Okay, and that's based on the trend. Okay, we'll go ahead and stop right here. We're almost done with section 1.1. Problem 10 is going to take some time though.